Alright, now I think we're ready to do the physical pendulum example, and I sort of hinted as to what are the main aspects of this problem. Our objective in this particular video is to write down everything we know about such motion and see how much predictions we can make, and that'll make us feel good about the physics we have learned. Now there is a fixed pivot, and we're going to take the x-axis in this direction and the z-axis in this direction. I'm sorry, y-axis in this direction, and the z-axis is perpendicular to the plane of the board. This point is the pivot point, and it's perpendicular to the plane of the board. How do we show it? We generally show it like this, coming out of the board and perpendicular. I thought we got this right. This means perpendicular to the board and getting into the plane. This is coming out of the plane, z-axis. Okay, so everything is all fine. We have a pivot point, we have a coordinate system, and we have the scale which is going to do pure rotation about this pivot point. Mind you, this scale has got only one dimension, that is L, and now it is important for you to look up the table and find the moment of inertia for such rotation, pure rotation. I think what you will find in that table is that if the axis is at the center of mass, then ICM is equal to ml square by 12. But I think we are not interested in that. We are interested in this point in this example, and I think that towards the end it's ml square by 3. So we got the formula for the moment of inertia, and the reason we're interested in that is because we're interested in this formula of pure rotation. And just to remind you, pure rotation, the key formula is tau is equal to I alpha. Everything looks perfect. We want to predict alpha, and tau is what we can easily calculate. And already we are interested. There's something new here in this example, and that is why it becomes a very important example. So what are the external forces on this? Yeah, surely one should never underestimate the importance of this first step, which is to draw the free body diagram. Now, too often we don't realize how important it is. So let's try to visualize the external forces on this scale. Now, there is a force coming from the pivot onto the scale, and what color should I use? Okay, red. So there is a force coming from the pivot onto the scale. All we can say about this force, external pivot, is that it is in the xy plane. So we are always going to assume that it's in the xy plane. Now this is consisting of one force maybe in the x direction, and one force in the y direction. So we can split up this force into two forces, Fx and Fy. So these are external forces coming from the pivot onto the scale. So but what is the other force? The other force is due to gravity. Now I'm going to there is an example in the first edition. I think it's example 6.7. I don't remember the page number, in Kleppner and Kolenkow, where he gives a beautiful proof of what is the torque due to gravity. Now, the point here is that there are a lot of particles. It's a system of particles. Don't forget that the scale is a system of particles. Okay, and if it consists of large number of particles, let's say this one, and so many other particles, now all of these are having a tiny forces distributed all over the scale. Let's say this is m1g, this is m2g, m3g, and so on. Now what is the torque due to gravity due to all these forces is the same as one single force acting at the center of mass. So how much force? The total mass into g. Now this is a result that can be easily proved. Like I said, you will find the proof in very nice and simple algebraic proof in the first edition, example 6.7 KNK. Now let's take that for granted. Now things are getting a little messy here, so let me just do it quickly all over again. I have a free body diagram of a scale which is undergoing pure rotation due to a pivot at this point, and there is a force from the pivot onto this, which consists of two components, fx and fy. This is coming from the pivot, and then there is a single force here acting at the center of mass, acting at the center of the scale, the center of mass, and equal to m into g. And let's not forget that this is the origin. Okay, so this is the origin, and therefore we can find the torque due to gravity. Oh, sorry, torque due to total torque on the system. So total torque on the system is equal to torque due to Fy, and then there is another torque due to Fx P, and there's a third torque, so plus there's a third torque due to the gravity mg. So now this clearly is 0 because the two forces Fx, Fy and Fx pass through the origin. So this is also 0, both the forces passes through the origin. And now this one, like I said, okay, let's keep track of the theta now. So this is the theta that we are trying to predict. This is theta as a function of time, and we'll take this as theta is equal to 0. So anti-clockwise positive. Now what is the torque? Torque is negative. I think we've done this. Now this is L by 2. Okay, and this distance is L by 2 sine theta. So the total torque is, okay, I just write it here, mg into L by 2 sine theta t at that instant of time. Okay, this is the torque at that instant of time. This is equal to torque at that instant of time, external. Okay, now this according to the law is equal to I, which we happen to know, into d square theta t by dt, and we are done. Okay, so this is now a matter of substitution if you want. M g L by 2 sine theta by theta at that instant of time is equal to I, which is m L square by 3 into d square theta by dt square. So you can cancel m, and then you get 3g by L. Everything seems okay. 3g by L 2L, and sine theta t is equal to d square theta by dt square. And somewhere I have convinced you that this can be solved, and you can get from here theta as a function of time, and therefore omega as a function of time. Alpha, of course, is already there. Of course, you can get alpha as a function of time. So things look good, and we are very happy. We have a lot of predictions to make as a function of time, but we're not done yet, and that's really the key part of the story. So we're not done yet. So let me see if I can remember this equation. 3g by 2l sine theta. Okay, so here we go. 3g by 2l sine of theta t is equal to d square theta t by dt square, can be solved to get theta of t omega of t. Let me write it neatly. Alpha of t, and things look very good. We seem to have made a lot of predictions, but we're not done yet. Right. So solving this equation is obviously not easy, but you can depend on the computer. Okay. However, maybe I should just make this. Oh, I think I have done the same mistake again. The torque is negative. Oh, whoa. I should put a minus sign here. Okay, so here we go. I have to follow the sign convention. Nothing, no big actually, it is a big mistake, but nevertheless, we can correct it very easily. There's a minus sign here. Okay, so here we go. D square theta by dt square is equal to minus 3g by 2l sine theta. Now, you perhaps are aware of the fact that if theta is small and in theta is in radians, then you can replace sine theta with theta. And actually, we come to an equation that is going to be very popular with us very soon. This is called simple harmonic motion, and we are going to make a lot of predictions. This particular equation is easy to solve, and solving this equation is going to be very important for us, and we can get all of them in a jiffy when we learn that. And that topic is going to be simple harmonic motion. Don't worry about this right now. Now we're not done with it. We do have another equation with us, and often in the beginning we tend to forget that we have this equation. Often we tend to think it's not important, but it's deadly important, as we will see, because many interesting questions are based on another equation that we have, and that is like this: for any system of particles at any instant of time, we have a beautiful equation which says force external time on the system at any instant of time has to be equal to rate of change of momentum of the system with time. Now, this one form of this is mass of the system into acceleration of the center of mass. So force external on the system at any instant of time, mass into acceleration at that instant of time. Now, this is such a beautiful and simple equation. We've exploited it a fair number of times before we got to this chapter, but I think we need to see whether if we invoke this, we get something interesting in this problem. So let's get back to the so-called physical pendulum. We are in a happy state of mind. We already have made some beautiful predictions. How about using this equation and seeing whether it implies something? Okay, now what I'm going to do is a couple of standard manipulations, or I think standard moves. We're going to freeze time. Okay, just completely freeze time, and let's say we have some magical powers, and this is the freezing time. There are some things that are already clear to us. Okay, theta is a function of time frozen there, and then we know the origin, we know the axis, and so on. And at that time, what we're going to do is try to use this equation, which is that there is a center of mass here, and we know for the scale, for example, it's at a distance of L by 2 from one end by symmetry. And the key observation is that we seem to know that it moves in a circle. Now, this is familiar territory. When something moves in a circle at a constant radius, we have a formula for the instantaneous acceleration, and I can write here, it's towards the center, its acceleration towards this radial is equal to mRL by 2 omega t whole square. Mind you, L by 2, because the distance from the origin is L by 2. And we also know that the tangential acceleration is going to be so tangential acceleration. Okay, so I am not following the sign convention. I think I should follow the sign convention now. Many of you have already pointed out that I should follow the sign convention. So what is the tangential acceleration? It's going to be in this tangential direction, and it's going to be r into alpha. Okay, I just write it as alpha at that instant of time, but you know that alpha is d square theta by dt square. So we know these two, and now what we will do is use this equation of ours and see what we get. F external on the system is equal to mass into acceleration of the center of mass. Mind you, we are keeping our eyes on the center of mass. In fact, this acceleration is composed of two components, AT and AR, which we are pretty confident about because the radius is constant L by 2. Alright, so the question is, what is the force external on the system? Now, like I said, I'm going to freeze the clock here, but now I'm going to choose a different axis in this frozen time. At this instant of time, I prefer an axis coordinate system like this. I think you know why, because this points down to the tangential direction and this points to the radial direction, so it seems to me that that's a good axis, instantaneous axis. So here's the significance of freezing time. So with this axis, what is the force? I mean, I don't know, frozen, how should I write frozen? Frozen x and frozen y. Okay, let me see what is the force in the direction of the frozen y. Okay, so the pivot force in the y direction of frozen y. So how do I write this? Okay, pivot force in y star. Okay, where y star is the frozen y, right? Plus now there is another external force in this direction, and so let's draw that. That's due to gravity here. Gravity is acting here. It can be split into two components, one like this. See, I'm getting the arrows right. One like this. Mind you, this is theta at that instant of time, and so it's now, if I'm writing force towards the center, I should put a minus sign here. I'll put a minus sign here, and this is mg, so this is going to be mg cos theta at that instant of time, frozen time. Okay, great. Now this, by Newton's law, is the force in the frozen y star direction. This is the equation I'm using. I won't keep repeating again and again. This is equal to mass into acceleration in this frozen is actually AR, which we know is L by 2 omega square t. We've written down this equation, one of these two equations. There are two equations here, and this is truly a wonderful achievement. Simple but beautiful equation by freezing time and using Newton's laws. Now we can do this one more time, and this time in the frozen x direction, which seems to coincide with the tangential direction. So once again, there is a force from the pivot. So frozen x star, force from the pivot at that instant of time, plus, now once again minus. I'm sorry. So you please make sure that you got this. Okay, I think I got it right. It's minus, and the reason this is minus is, I'll tell you, it's here, right here. See, it's like this, opposite to the force of the pivot that I've written as positive. So force of the pivot minus mg sine theta at that instant of time is equal to mass into acceleration, which happens to be r alpha t. and here's my second equation. So what is the achievement here? I think you've already realized it. From the previous discussion, we are confident about cracking down on theta, omega, and alpha if you want. And now, with the help of this equation, this is the gift of this equation. Like I said, we keep forgetting to use this equation, but please note how we've also used rotational kinematics that we did a couple of videos ago. Now what's this? What is it that we're able to predict? Fairly easy to know. Think that this is known, this is known, this is known, this is known, and so this becomes predictable. Same thing here, this is known, this is known, this is known, and this becomes predictable. And therefore, let's add to our list of victories: theta t, known; omega t, known; alpha t, known; force in the radial direction of the pivot, known; force in the tangential direction from the pivot, if I could say, force on the scale from the pivot, force, okay, I just want to write this down, force on the scale from the pivot in the tangential direction, okay, tangential direction, and this is the radial direction. So just want to write it: external force, sometimes call it the force of reaction from pivot onto scale. And by Newton's third law, if somebody asks you what is the force by the scale on the pivot, just reverse the direction, right? So I'm not going to write this all over again. So this is also known. So basically, just to repeat, we had two equations, one from our first term, first half of the physics that we learned, and we kept doing lots of problems just with this particular formula. And today we are saying that it's still very useful because it's giving us this predictions, giving us this prediction. And the other is what we have gained from tau is equal to L dl by dt, which for pure rotation morphed into for our simple problem of forces in the xy direction and so on, morphed into tau z is equal to I alpha t. Okay, so this is the equation that we used, and together these two form such a perfect, wonderful pair, and they gave us all of this. And I hope you can see that how powerful we've become by adding one more law to something that we learned in the beginning of the term. So once again, there are two things we have learned which are independent laws for a system. This is the first one, and we tried to dwell on this for a long time. And this is F external on the system. And today we had another equation, torque on the system external, which nicely looks very symmetrical to this dl by dt of the system, and at any instant of time. This is always true, like we said, and these are all vectors. And but we said we look at a simplified situation for this, and this translates to tau for pure rotation. I'm sorry, we still not got into fixed axis rotation. For pure rotation, this law can be stated in this form: tau z is equal to I alpha t. And so we can say that these two have been beautifully exploited together. That's the point, together, to make predictions about alpha t, omega t, theta t, and then from there on also the F external reaction forces from the pivot. Okay, now before I close down, I think I just want to tell you that implicit in this, and we have done this so many times, but I think it's worth repeating, it is understood now that you know alpha. I mean, this is a part of information given in the problem. Theta at 0, that is the initial theta, and omega at 0 are to be given. Okay, now I'm just stating it at the absolute end. Didn't want to interrupt and keep giving you the same information again. Please note that this is absolutely essential information. Sometimes it's also written as theta 0 and omega 0. Let's not forget that this is given to us, and that is why with confidence we are saying that I'll tell you all of it is. So with that, we can close this problem, and I think I would like to do the Atwood machine in the next problem. All right.